Good morning. So, in the previous lecture, we have discussed about the need for multi-compression system, need for particularly the multi-stage systems. Okay, and in multi-stage system, if we have large temperature limits, then we have to operate in a multi-compression manner. Okay, we have to use multiple compressors, and if there is requirement of multiple evaporators, like we have requirement of cooling at different temperature conditions, then we have to operate with the multi evaporator system. And the third category of system is actually cascade system. So cascade system is basically used when our temperature limits are excessively large, so that I'll discuss subsequently. Other than that, for multi-stage systems, we have to get ready with some of the few components, some of which were nothing but flash chamber. Then we discussed about the intercooler, water intercooler, and third category we have the nothing but flash chamber as intercooler. Now we can also have one more additional component which is called as liquid subcooler. Okay, so maybe liquid subcooler right now I'll not discuss. Whenever we will be discussing the complete system at that time only I will describe. Okay, so now let us start with our discussion on the multi compression, particularly two stage compression system. And in this multi compression system, what we will do, we will use flash chamber. Okay, secondly we will use water intercooler, and we will also use flash chamber as intercooler, so it means flash intercooler. Is this point clear what I said? Okay, so I'll be using multi compression, particularly the two stage compression system. And in this two stage compression system I will be using flash chamber. So flash chamber is for the purpose of removing the vapor from going it into the low stage. Okay, and then second is water intercooler. So we will be using the heat exchanger for intercooling, where water is used as the cooling medium. And third is we will also integrate along with water intercooler flash intercooler. Okay, the benefit of flash intercooler is that with water intercooler we will be again ending up in reaching the superheated state, but with flash intercooler we can ensure that we are coming up to the saturated state. Is this point clear? So how we will be integrating this system, let us understand. So first I will be having condenser. Of course the condenser will be the high pressure equipment, and this high pressure equipment will be then connected to an expansion device, as we have to deploy over here the flash chamber. So that's why the first expansion device we have to use is nothing but a float type expansion device. Is this point clear? So first expansion device will be nothing but a float type expansion device. From the flash chamber at the bottom, then we will be taking out saturated liquid, and this saturated liquid we have to again pass through another expansion device. Okay, and this expansion device then will be bringing the pressure and temperature conditions which are required at the inlet of the evaporator. So then I will be having evaporator over here. After the evaporator I will be having actually my first compressor. Okay, so this is the first compressor, and after first compressor what we will be having, because we have to use what, water intercooler. So immediately after the first compressor, now I will be having some heat exchanger over here which will be working as the water intercooler. After water intercooler I have also mentioned over here that I do have flash intercooling as well. So for achieving flash intercooling, this fluid I have to directly dip into the flash chamber, and then from the top of the flash chamber I have to take out all the vapor, because I have to maintain the pressure constant under the steady state conditions in the flash chamber. So I will be taking out this vapor, and this vapor will be mostly at the saturated vapor state, and this vapor then I will be passing through the what, second compressor, and then it will be going into the condenser. Is this one here? So This will be my now system. So now in this system here I am having liquid refrigerant in the liquid state, and typically at this point I do have nothing but saturated liquid, and at this point I will be having saturated vapor. All are clear with this? Now if I consider that the thermodynamic state at the exit of evaporator is 1, state at exit of first compressor will be 2, the state at the exit of water intercooler is 3, state at the exit of flash chamber, particularly the saturated vapor state, is 4, this will be 5, exit of condenser is 6. Then at this particular point, which is coming after the first expansion device, this will be state 7, and corresponding to this my pressure has to be intermediate pressure PI, and then this saturated liquid is at state 8 and this will be at state 9. So all are clear with this block diagram for the two-stage compression system with flash chamber, water intercooler and flash intercooler. Okay, so this is my flash chamber, this is water intercooler. So in the water intercooler from other side I have to supply nothing but cold water for exchanging the heat so that I can actually intercool the refrigerant. And of course, because I am also using the flash intercooler, so whatever is coming at the exit of the intercooler, that has to be again supplied to the flash chamber. And in the flash chamber, I will be having this vapor, and this vapor in the form of bubbles will be rising in the upward direction. Is this one clear? And ultimately from the top of the flash chamber I will be taking out saturated vapor state. Okay, anyone is having doubt in this block diagram?
Sir, why are we using
All of these together because if I can integrate all the components together, you will be able to understand. And another important aspect is whenever we do operate with certain refrigerants, okay, for example, if I operate with ammonia, then this type of combination is required. If I operate with some other refrigerant such as R12, then I can take out some of the components. I can operate in some different configuration because each configuration has its advantage and disadvantage. Okay, I told you yesterday that whenever I will be using the flash intercooler, then the top compressor has to handle extra mass of vapor. So that extra mass of vapor sometimes can actually result in additional limitation that it will be consuming almost equal amount of work as was there without intercooling. Okay, but particularly for ammonia system, the additional work which will be coming because of extra mass, that is very small and it leads to savings in work. But if I operate flash intercooler for the R12 refrigerant, then it will be again that type of limitation will become severe. Okay, so that is why different type of system we operate. If we are having different type of refrigerant, these we operate in different configurations. Over here I am not specifically expressing that I am explaining for which refrigerant. In general I am trying to explain a system which is having all the components integrated together. Is this one clear? Now what we need to do? What is next task? We need to draw the pH diagram of the system. Okay, so can you now draw the pH diagram, because all of you know all the processes? Please tell me, can you draw it? First thing you need to consider is I have 3 pressure conditions. So draw 3 lines. Okay, bottom one is evaporator pressure PE, this is intermediate pressure PI, and the top one is condenser pressure PC. Now if you follow, state point 1 represents the saturated vapor state at the exit of the evaporator. In a standard cycle it will be saturated vapor. So this is my state point 1. Okay, 1 to 2 is first stage compression, which is an isentropic, and it increases pressure from evaporator pressure to intermediate pressure. So this will be my 1 to 2. Now at point 2, what I am doing? I am passing the substance through an intercooler in which the working fluid will be losing certain amount of heat. Okay. So after losing heat, say it has reached to state 3. Is this one clear? So 2 to 3 is the cooling of the working fluid in the intercooler. Then what I have done? At state 3, I have supplied the working fluid into the flash chamber. When I supplied into the flash chamber, then these bubbles of the vapor state has come out, and these bubbles have come in direct contact with the liquid. So you know, generally whenever we do heat exchange, what we are having? We have in indirect or non-contact type medium, we will be having a cold medium flowing outside the tube. We will be having a hot medium flowing inside the tube. So whenever from hot medium to cold medium heat will be transferring, it has to overcome the conduction resistance of the tube wall. Okay, but in this scenario, I am directly allowing the vapor to come in contact with the liquid, where vapor is my hot medium and the liquid present in the flash chamber is my cold medium. It means it's a direct contact type heat exchange process. Okay, so in direct contact type heat exchange process, there is no additional conduction resistance of the tube wall material. That's why the heat transfer rate in this type of system is even faster in comparison to the indirect contact type. Is this one clear? Another important point is the maximum amount of cooling can happen in this is up to basically the saturated state. Of course, saturated state does not mean that I have to stop at this point only, because if a bubble is rising and if its sensible energy is removed, then first it will be reaching to saturated vapor state, and say somewhere over here its sensible energy is removed. Then after this, whatever journey it will be doing, there it will be losing its what? There it will be losing its latent heat, and if it loses its latent heat, its size will keep on decreasing. But we don't want to do that. What we want to do, that we want to operate in such a way so that ultimately I should reach at point 4. Though it's challenging to exactly come to point 4, but still we try to control the flow rate in such a way so that I can reach up to saturated vapor state. Is this point clear? Anyone is having any doubt about this? Then if it went up to saturated vapor state, then from the top, whatever vapor was there on the in the chamber, that vapor actually I have taken out at state 4, and I have passed through the second stage compressor. So in the second stage compressor, again there will be isentropic compression from 4 to 5. Okay, then I have passed it through the condenser. In a standard condenser, what will be having? I will be having cooling up to saturated liquid state. So this is 5 to 6 process. Then 6 to 7, I have done what I have done? I have done flashing. I have done expansion. And in this expansion process, there will be, which type of expansion is this? Isenthalpic. So my line will be a constant enthalpy line, and this is 0.7. So 0.7 is a mixture. It means some liquid during this expansion process has converted into vapor. But after that, what I have done? I have designed the chamber in such a way so that all the saturated liquid is collected at the bottom and all the vapor, saturated vapor, is collected at the top. Okay, so it means that this 7 state is actually not physically existing. We do not have any substance which physically having the properties identical to that of state 7. But state 7 is actually average of entire liquid and vapor mixture. But if identically I look into the liquid and vapor, then liquid will be corresponding to state 8 and vapor will be corresponding to state 4. All are clear with this point? Okay, so when I do the flashing from 6 to 7, then whatever the value of enthalpy I am getting, that enthalpy is actually the mass average of the mixture, liquid plus vapor. But there is no substance which is physically existing as a mixture. Physically what we have? In the chamber, liquid at the bottom and vapor at the top. So that liquid will be corresponding to saturated liquid state, which means state number 8, and vapor will be corresponding to saturated vapor state, which is state number 4, at the same intermediate pressure Pi, because pressure of both liquid and vapor in the chamber is same. Is this point clear? This point has to be understood with clarity. So it means that from here I can say that there can be two arrows, which will be, one will be giving me pure liquid, other will be giving me pure vapor. Okay, and what process these arrows are representing? These arrows are simply representing the gravitational stratification. I am not doing any process. This is just a gravitational stratification. Liquid being high density settles at the bottom, and vapor being lighter settles at the top. Point is clear? Now, from the bottom of the tank, I have actually taken out the substance. So, if I take from the bottom of the tank, I am taking out nothing but saturated liquid. So, it means I am taking the liquid at state number 8. Now, again I am using an expansion valve which is decreasing the pressure up to the evaporator pressure PE. So, here I will be having then again isenthalpic process up to state 9. Is this point clear? Now you can understand the benefit of flash chamber is that if you do expansion without flash chamber, then you could have ended up in some point over here. But using the flash chamber, you have come to this point. So this much amount of throttling loss you have saved, and you have led to significant increase in the specific refrigeration effect. Is this point clear? So 9 to 1, again there will be process in the evaporator. Now, let us understand few more intricate details. First point is, whenever this vapor is rising in upward direction, if the velocity of this vapor is very large, then what will happen? This vapor can also take out some liquid droplets along with it. Is this one clear? So if the vapor which is coming from the bottom, and if this vapor is actually sucked at very high velocity, then what will happen? Whenever a fluid moves at very high velocity, some liquid also attaches to this. Okay, so it can carry certain amount of liquid along with it. But the entry of liquid in the compressor is always detrimental. It may lead to cavitation, and it may lead to erosion because of the high momentum of liquid droplets. Whenever these will be striking against the wall, cylinder wall, these will be leading to erosion of the material. And third important point is, we understood that we are operating reciprocating compressors, so we have to use lubricating oil, and lubricating oil has more tendency to mix with the liquid, again which will be detrimental for the life of the compressor. So it means that here we have to control the velocity of this vapor in such a way so that it should not be able to carry the liquid droplets with it. Okay, so typically the vapor velocity is kept less than equal to 1 meter per second. Okay, generally this velocity has to be less than equal to 1 meters per second. If it is more than 1 meters per second, we will be having actually this issue. Is this point clear? Anyone is having any doubt about this? Okay. Other important aspect is, flash chamber is very important component. Now from this system, can you tell me, my both compressors are handling same amount of mass flow rate of refrigerant or different amount of refrigerant? Please tell me, both the compressors, compressor 1 and compressor 2, are they handling same amount of refrigerant mass flow rate, or is the refrigerant mass flow rate different in the two compressors? Different. Okay, so let me consider that m dot 1 is the mass handled by the first compressor, and m dot 2 is the mass handled by the second compressor. Okay, Now, what are the additional mass which are coming on the second compressor? Can you tell me? What are the additional mass?
The mass of that vapor coming from the first process.
Yes. In 6 to 7 process, what is happening? I have formation of mixture at point 7. Okay. In which some amount of vapor is formed which is collected at the top. That vapor I have to continuously remove, otherwise what will happen? Chamber will be overpressurizing. Okay. So it means first is the mass of vapor formed due to flashing. Is this one clear? This is nothing but the mass of the vapor which is formed due to flashing process. All are clear with this point? What is the second type of mass?
The liquid that is evaporated.
Yes. Now you have to understand one very important point. Whenever this vapor is entering into this substance, okay, so it is being cooled from state 3 to state 4. Whenever it is being cooled from state 3 to 4, it means it is losing some amount of heat. Ultimately, where that heat is going, so these were the vapor bubbles which were having higher temperature, and that heat is going into the liquid present in the flash chamber. That liquid is in which state? It is in saturated liquid state. So whatever heat it will be gaining, it will be gaining heat in the form of its latent heat of vaporization. From 3 to 4, there is sensible heat loss. So vapor bubble is losing heat in the form of its sensible heat. That's why its temperature will decrease. But the substance to which these vapor bubbles are giving heat, that is in the saturated liquid state. So whenever it will be gaining heat, if we have saturated liquid and we start heating the saturated liquid, what happens? Phase change occurs. So because of this heat transfer process, some liquid will be converting into the vapor. So I will be having additional mass of vapor due to evaporation, or due to, I can, let me write it, yeah, evaporation of liquid. Fine. So some liquid will be actually evaporating into the vapor state. Is this point clear? Anything else? Other than this, of course, from the bottom, I am getting m dot 1 mass. So that m dot 1 mass also it has to take out. Okay. So mass flowing through compressor 1. Is this one clear? Whatever is coming through compressor 1, that though it has to take it out. Okay. Okay. Now can you do the thermodynamic analysis of this cycle in order to determine its COP and what is the relation between M1 and M2, how to determine what will be M2. So for M2 I must calculate mass of vapor formed due to flashing and mass of vapor due to evaporation. So can you tell me how I can proceed for thermodynamic analysis? Please tell me. Okay, let me first start with the process number 9 to 1. Okay, in process 9 to 1, if my RE is the refrigeration effect, that has to be equal to m dot 1, which is the mass handled by the first refrigerant, into H1 minus H9. All are clear with this point? So this is the mass handled by the so from here, if I know that for how much tons of refrigeration I need to design the system, then I will be knowing this left hand side. I know H1 and H9 from the given pressure condition. I will be able to calculate m dot 1. All are clear with this? Now let's go to flash chamber. It's a very, very important component. And let's draw a control volume around the flash chamber. Okay, so I have drawn a control volume around the flash chamber. Now you tell me, across the flash chamber, under the steady state conditions, there should be mass and energy balance. Is this one clear? So if I am operating under the steady state condition, then level of liquid in the refrigerant should remain at the same location. It means mass should be balanced. At the same point of time, if I assume that my flash chamber is perfectly insulated, then whatever energies are exchanging, these should also balance with each other under the steady state condition. Of course, during the transient operation, there will be fluctuations. Okay. So, in this control volume, there has to be mass balance as well as energy balance. Now, let us identify what are the different inlet streams and exit streams. So, this is first inlet stream to this control volume, and this inlet stream is coming with m dot 1 mass flow rate. Is this one clear? This inlet stream is coming with what mass flow rate? M dot 1. There is another inlet stream from here, from point number 6 to 7, and this inlet stream is coming with what? M dot 2, because after compressor 2 I do not have any component where bifurcation of the mass is happening. Okay, so at this point mass entering to flash chamber is m dot 2. Is this one clear? Now let us focus on the exit streams. If you see exit streams, I have one exit stream over here which is coming from point 8, and whatever is coming from point 8, same mass is passing through this compressor. So it means mass coming out of 8 is nothing but m dot 1, and whatever is going out of point 4, that is actually the same mass which is entering into the compressor. So it means this is m dot 2. All are clear with this point? Now you can clearly see that m dot 1 entering at point 3 and m dot 1 leaving at point 8. M dot 2 entering at point 6 and m dot 2 leaving at point 4. Is there mass balance? There is mass balance. M dot 1 plus m dot 2 mass is entering the flash chamber, and m dot 1 plus m dot 2 mass is leaving the flash chamber. Now let us write the energy balance. If I write energy balance, this m dot 1 mass is entering with what enthalpy? H3. It is entering with H3 enthalpy. So let me now write energy balance across flash chamber. So m dot 1 has entered with enthalpy H3. Other thing, what is entering? M dot 2, and m dot 2 is entering with enthalpy 6 or 7, whatever it is. If I just consider flash chamber as control volume, then 7 point is after the throttling process. Okay, so after the throttling process enthalpy should be 7, but 6 to 7 is an isenthalpic process, so enthalpy will be same. So let me write plus m dot 2 into H6 only. Why H6? Because H7 state is coming in between the liquid vapor dome. So calculating enthalpy at that point will be little bit more difficult, because one should know dryness fraction. But calculating enthalpy at point 6 is very easy. Saturated liquid state, so directly from the saturation table I can calculate. So m dot 2 into H6. Clear? This is the energy inlet. What is energy out? M dot 1, it is leaving at which state? State number 8, which is a saturated liquid state. Okay, So m dot 1 into H8 plus m dot 2, what is the state? H4. Clear? H4, saturated vapor state. From here, if I segregate m dot 1 and m dot 2, m dot 1 into H3 minus H8 will become m dot 2 into H4 minus H6, and from here I can calculate that m dot 2 is nothing but m dot 1 times H3 minus H8 divided by H4 minus H6. Okay, if you see now, what is H3? Enthalpy at the exit of the water intercooler. H8, enthalpy, saturated enthalpy at intermediate pressure, saturated liquid enthalpy. H4, saturated vapor enthalpy at intermediate pressure. And H6 is what is H6? Saturated liquid enthalpy at condenser pressure. Okay, so I know all these enthalpies easily, so I can calculate the value of m dot 2. All are clear with this point? You can also see that what is H3 minus H8 on pH diagram. H3 minus H8 is this distance. From here to here is H3 minus H8. And what is the other one? H4 minus H6. So you can see H4 minus H6 is this difference. It is H4 minus H6. So from pH diagram you can see that H3 minus H8 is greater in comparison to H4 minus H6. It means this ratio will always be greater than 1 and m dot 2 will always be larger than m dot 2. Clear? This is very important point. M dot 2 will always be larger in comparison to m dot 2. Simply from the enthalpy pH diagram itself, by just seeing the linear distances, I can actually express this. Okay. Now what will be my work of compressor or net work input to the system? Of course, only compressor is the work consuming device. So work input will be m dot 1 into
H2 minus H1.
plus m dot 2 into
H5 minus H1.
H5 minus H4. Okay, and ultimately I can simply calculate my COP of this system as nothing but what is refrigeration effect? M dot 1 into H1 minus H9 divided by work is m dot 1 into plus m dot 2 I can write nothing but m dot 1 into H3 minus H8 divided by H4 minus H6 times H5 minus H4. Okay, ultimately m dot 1 I can take common, so COP will simply be H1 minus H9 divided by H2 minus H1 plus H3 minus H8 divided by H4 minus H6 times H5 minus H4. This is nothing but my COP. All are clear with this point? Anyone is having any issue? Okay? Everyone is fine with this? So this is how I can simply easily analyze this system. Now whatever configuration I give to you, you should be able to analyze that configuration. Okay? Now let me also try one more thing. Let me also express the mass this energy balance in slightly different way. Okay, so basically what we have two components over here. One is because of flashing and other is because of intercooling. So if you want to segregate out how much amount is coming because of flashing, energy content which is coming because of flashing, and what energy content is coming because of intercooling, that also you can segregate, but you have to balance or place the energy balance in slightly different way. Maybe I'll not discuss now. So what you do, uh, all of you now also apply energy balance by simply considering individual masses rather than m dot 1 and m dot 2. You can divide this into m dot 7, and then from m dot 7 you can write m dash is converted as vapor mv. So likewise, if you apply energy balance, you will be able to even find the individual components of energy, how much energy load is coming on flash chamber because of the flashing, and how much energy load is coming because of the intercooling. Okay, maybe or subsequently I will discuss further. All are clear with up to this point? Now, if I can give you any configuration of this system by just doing small alterations, can you solve this? One easy configuration could be, I will simply say that I am removing the water intercooler. So if I remove the water intercooler and directly use flash intercooler, then everything will directly go inside. Is this one clear? Everything will directly go inside, and from 2 to 4 process will happen inside the flash intercooler. Okay. Other configuration could be, I say that I am using the flash chamber, but I am not using flash intercooler. If I don't use flash intercooler, only use water intercooler, then what will happen? Sorry?
No flash gas.
I am using flash chamber, but I am not using flash intercooler.
7 to 4. 7 to 4.
7 to 4 will?
Not
No, it will happen. Okay. 3 to 4 will not happen. Yes, 3 to 4 will not happen. 2 to 3 will happen. But then what will happen to 4 and 3? How I will be compressing this? Sorry? How I can compress them? Okay, so let me now use the previous configuration only. Again, two-stage compression, with flash chamber and water intercooler. Please tell me, what should I do over here?
डायरेक्ट 2 और 4 को मिक्स कर सकते हैं.
Direct 2 and
The gas which is coming at PI from flash chamber.
3 and 4.
3 and 4.
3 and 4. Okay. Okay, so in this process, let me only explain the pH diagram. I will not draw the full block diagram. Okay. But what will happen, what changes will happen in the block diagram, that let me explain. 2 to 3 process will happen in the water intercooler. But after this, I cannot enter it over here. And from here, I have to take out saturated vapor at state 4. So 4 and 3 I can mix together before passing through the compressor, because the pressure at point 3 is also PI, pressure at point 4 is also PI. If both the things are, two streams are at same pressure, I can easily mix these together inside a mixing chamber. Okay, and then when these two will be combining together, state 3 is having superheated enthalpy, state 4 is having saturated enthalpy. When these two will mix together, these will exchange heat, and final enthalpy will be somewhere in between these two, and that will be my state 5. Okay, so let me draw the system also. So now I am not using flash intercooler, only flash chamber and water intercooler. Quickly let me draw the system as well. Shall I draw or shall I leave it? State 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Clear? What will be pH diagram? You should be able to explain it now. Same. There will be slight difference, huh? This is from 1 to 2, then 2 to 3. Here I will be having 7 to 8, and 8 to, this is 4 and 8 to 9. Then 9 to 10 and 10 to 1. Okay. And here 4 and 3 are mixing together inside a mixing chamber. So therefore their enthalpy will come to some middle state in between 0.3 and 4. So somewhere over here I will be having 0.5, and from 5 to 6 I will be having the compression process. All are clear with this point? Now let's try to do quickly the thermodynamic analysis. You should be able to do now. I should not explain it again, but let me quickly write it. What will be refrigeration effect? Please tell me. M dot 1 into H1 minus H10. What will be mass handled by the higher compressor? It will be mass of passing through first compressor plus mass of flashing, additional mass which is coming because of the flashing. How much additional mass is coming because of the flashing now? What I need to do? Draw control volume again quickly. Apply energy balance. What will be energy balance? Please tell me. What is entering into this? M dot 2 is entering. From here what is leaving? Only M dash mass is leaving. From this point only M dash is leaving. And from here what is leaving? M dot 1. Okay. So what will be energy balance? M dot 2 is coming with enthalpy H7. Okay. And leaving is M dot 1 is leaving with H9 plus M dash is leaving with H4. M dot dash again in the flow rate form. Okay, and second thing, I can also write the mass balance. What will be mass balance? M dot 2 is mass entering, M dot 1 is leaving plus M dot dash is leaving. From here m dot dash will become equal to m2 dot minus m1 dot. Okay, all are clear to this point? So let me substitute m dash over here in the energy equation. If I substitute in energy, then I'll be getting m dot 2 into h7 equal to m dot 1 into h9 plus m dot 2 minus m dot 1 into h4. From here, if I segregate, then m dot 1 into h4 minus h9 will become m dot 2 into h4 minus h7. Have I written it correctly? Please check it. Have I written correctly or not? M dot 2 will become m dot 1 times h4 minus h9 divided by h4 minus h7. Now you can see h4 minus h9 is this on pH diagram and h4 minus h7 is this. Again, h4 minus h9 is greater in comparison to h4 minus h7. It means m dot 2 will always be greater than m dot 1. I calculated m dot 2. Now what will be my net work of compressor? M dot 1 into h2 minus plus m dot 2 into h6 minus h5. Let me write down the COP. Please quickly write it. M dot 1 into h1 minus h10 divided by m dot 1 into h2 minus h1 plus m dot 2 I can write m dot 1 times h4 minus h9 divided by h4 minus h7 times h6 minus h5. Okay, and from here again m dot 1 I can take out common. It will be h1 minus h10 divided by h2 minus h1 plus h4 minus h9 by h4 minus h7 into h6 minus h5. Is this one clear? Anyone is having doubt? Okay. Another interesting point is, can you tell me how to calculate enthalpy of 0.5? How to calculate enthalpy of 0.5? This is again an issue. Okay. What I can do? I can draw a control volume about point. This junction. This is nothing but a mixing chamber. So in this mixing chamber, what I am getting? M dash mass is coming at enthalpy H4. So I can write M dash into H4 plus what is coming? M dot 1 mass is coming with enthalpy H3. So M dot 1 into H3. What is going out? Going out is mass handled by second compressor, which is m dot 2, and it is going with enthalpy H5. So m dot 2 into H5. Now from mass balance across the compressor, I know that m dash is nothing but m dot 2 minus m dot 1. So this will be becoming m dot 2 minus m dot 1 into H4 plus m dot 1 into H3 equal to m dot 2 into H5. What is my aim? My aim is to calculate enthalpy of 0.5. So from here I can calculate H5 as m dot 1 into m dot 1 into H3 minus H4. Okay. What else? Plus H4, and this will be m dot 1 divided by m dot 2. All are clear with this or not? Okay. Please tell me. Now m dot 1 by m dot 2, it will be something in fraction. H3 minus H4 is again a positive quantity, and H4 is saturated vapor enthalpy. So it means from saturated vapor I will be slightly shifting to right. But whenever I will be shifting to right, I will be always in the left of H3. I will be able to reach to H3 when the ratio of m dot 1 by m dot 2 is equal to 1. Then it will be H3, but always m dot 1 will be less than m dot 2. So this ratio will always be less than 1. It means I will be always on the left of H3 but on the right of H4. So depending upon the ratio, I will be somewhere in between point 3 and 4. So 5 point will be between 3 and 4 depending upon the mass fraction ratio across compressor 1 and compressor 2. All are clear with this point? Anyone is having any doubt? Now let me give you one homework assignment. So you have to test a two-stage system, two-stage compression system, okay, with flash chamber and flash intercooler. There will not be any water intercooler. Is this one here? Two-stage compression system with flash chamber as well as flash intercooler. One interesting point is left. We have used some intermediate pressure Pi. Now what should be the optimum value of Pi? Of course, there is thermodynamic analysis for determining the optimum value of Pi. I am not going into the derivation of that thermodynamic analysis. Let me directly give you the final formulation. The optimum value of Pi for ideal gases and for ideal conditions is geometric mean of condenser and evaporator pressure. So square root of Pc into Pe. Whereas if I consider the real refrigerants and actual conditions, then one correction factor comes over here, and that correction factor is nothing but PCPE into TC divided by TE and entire square root. So this will be for ideal conditions and this will be for real conditions. We have done so much discussion, but we didn't identify what should we choose the value for intermediate pressure. Okay, so of course the detailed thermodynamic analysis, if we do mathematical derivation, that explains that under the ideal conditions it should be square root of Pc into Pe, but whenever some experiments are performed and it is found that under real condition it should be Tc by Te multiplier should also come into picture. Is this point clear? So now you should be able to determine the value of intermediate pressure. Okay, so let me stop at this point. We'll discuss further in the next class.